Now, so this is one of the most difficult things in astronomy, especially the observational astronomy, to spot extrasolar planets. Planets. Uh, but by now, in the recent times, the significant technological advancement that took place in the observational astronomy area, optical telescopes, radio telescopes, not only on the Earth, but in orbit like Hubble and other more recent ones. Therefore, we were able to see farther and farther away with much more clarity. And therefore, now observations, the new planets, exoplanets are actually now coming in. So this is not the latest statistics, but this was some time back. At present, there are 281 planets listed, and out of that, 277 orbiting normal stars. That is very intriguing. Normal stars. The first one was a planetary system, but those planets were not going around a normal star. It was a neutron star. So somebody might say, no, this is not very significant, because how can life exist on a planet that is going around a neutron star, right? But here our main discussion is not about life, it's about nebula theory. So therefore it's a strong evidence. But looking at the other side, we would be much more interested in finding planets that are going around normal stars. So what do we mean by normal stars? It's a star like ours, the sun, which actually support life. Okay. So 277 out of 281, they are normal normal stars, right? And out of that, 63 multiple planetary systems. So that is bad news, because as you know, when you have multiple anything, right, there are problems, right? In society also it's like that. When you have multiple leaders, you are in trouble. Okay. So multiple planet systems, there's always interaction, right? Always interaction. Especially these planets are big ones like Jupiter and Saturn. So in that area, it's difficult it's not very stable for other planets, right? And also, if you have multiple star systems, this is another problem. The gravitational field changes so intensely. So you're not on you're stable. You're not on a stable orbit most of the time. So if you look at the sun and our solar system, we are stable because we are single star system, and also inner part of the solar system, we don't have big planets, right? In our area, the gravitational field strength doesn't change so much. Okay, right. And out of that, we have 214 single planet system. This is very, very interesting. Single planet system means some sort of stability in the orbit. Okay. There you can see what we see are mostly single planet system, because in other words, they are stable. That is why we see so many of these things still exist. Whereas the other ones, multiple planet systems, they have short lives, because sooner or later they feel the unstable gravitational perturbations, and they are thrown out of their orbits. So they don't have a long life. So like that. So this is again not the latest, but it tells you the message, right? What is this? From 1989, this is where we first started to actually get observational evidence for exoplanets. Up until 2012, right? You can see the numbers going up. right? Number of detections, right? 2008, 9, 10, 11, 12, like that. These are yearly observations, not the accumulated, I think. Right? This is yearly thing, because that is why the graph sometimes goes down as well, right? And you can see this color information. If you look at the red ones, then you have the green ones, purple, pink, etc. So this color tells you in which method these planets have been detected. So there are a number of methods. What are they? Radial velocity, transits, microlensing, imaging, pulsar timing. So I think I explained you pulsar timing, right? I explained you pulsar timing. But there are other things, radial velocity, radial velocity. That is also something you can understand. Say, for example, you have studied about Doppler effect, right? This is the Doppler. This is Doppler. You have seen the traffic police pointing the radar gun at you, at the vehicles, and he immediately understand at what speed you are driving. Okay, this is the radial velocity measurement. Radial velocity measurement, right? So any radio frequency that is emitted by the moving object, okay, gets compressed if that object is traveling at you, and also the wave gets stretched when that object is uh, going away from you, from the observer. So if you know the wavelength or frequency, and if you know what you receive, then you can say whether that object is either coming at you or going away from you. You need to know what is that frequency, right? Exactly. And then the observation, anyway, the traffic policeman, right? He emit that radar frequency. Therefore, he knows what he emitted. And then he takes the reflected one, what is coming at you, right? So he compares the two things, what he emitted, what he receives. If what he receives is higher frequency, right, than what he emitted, he knows the vehicle is coming at you. Of course, he can see it. But the difference of the frequency tells the speed you are driving. Same technique is used in other fields in astronomy. You can actually check some of these frequencies. Okay, but unfortunately, we cannot send a radio frequency burst to a planet or a star and then receive the reflection and then check how much it has changed. That is not going to be the technique here, of course, right? But there are other methods for us uh, to use to figure out whether the stars are coming at us or going away from us, right? If you look at the spectrum or radio frequency spectrum coming from a star, right, we can check it, right? All these optical frequencies, infrared, and also the other side, low frequencies, right? And going to the high side to X-rays and gammas, right? Uh, so if you see a gamma ray here and gamma ray on another star or another Milky Way, another galaxy, gamma is gamma, right? And if you see any other radio frequency, optical frequency here or in Proxima Centauri or Andromeda galaxy, it's the same thing. It's not going to change. If you see hydrogen here or on Mars, on Jupiter, on Proxima Centauri, hydrogen is hydrogen wherever it is. It's not going to change. There's no like special hydrogen in Mars. There's no special hydrogen in the sun. Okay, they're all the same. Hydrogen is hydrogen, helium is helium, and so on and so forth. So if you get the spectrum of a star, right, you can understand what are the frequencies it is emitting. Okay. And if you get a spectrum of a star which is coming at you, at a speed, that spectrum and a very similar star which is actually not moving anywhere, not either coming at you or going away from it. If you compare the two spectra, right, then you will see the frequencies are shifting to one direction. Okay. The spectrum that you receive from the star which is coming at you, you will see the frequency shift to a high side. All the frequencies are shifted to high side. Okay, right. So I'm not going to tell you more than that about it, but you can understand the radial velocity measurement can tell you whether the stars are coming at you or going away from you. Now, if you see a star which is coming at you, right, right now, and after few hours it is not coming at you, and after another 1 hour it is actually going away from you, and after another 1 hour it is not going anywhere, speed is 0, and after another 1 hour it is coming at you. This is very interesting scenario. This particular star is coming at you and going away from you in a periodic manner. So how can a star perform a dance like that in few hours, few days maybe, right? Coming at you, going away from you in a periodic manner. Can somebody explain how is this possible? How is this possible? Any answer? Okay. So one possibility is that there is a big planet around it. Big planet that is going around the star. And this planet doesn't have any light. Therefore, we can't see it. It is farther away. Even this particular star is like a dot. And there's no way for us to detect directly that planet which is going around that sun, that star. But you can see, because of the gravity of this planet, this is a double body system, multiple body systems, right? Two bodies, one is the star, the other one is the planet. So when they spin around each other, right? The planet goes around the star goes around the planet, something like that. In fact, they are rotating around the common center of mass. Common center of mass. Don't think that the sun is at the center and everything is going around it. That is not physically correct. If you see the entire solar system, there is a common center of mass. Common center of mass, and everybody is going around that. Okay. So here there's a star, there's a big planet, and let's assume it's comparable in the magnitude. So therefore, the star, right, when it is moving around the common center of mass, part of the journey, the star is coming at you. The other part of the story, the journey, it is receding, going away from you. And that is why you periodically observe the star is coming at you and going away from you. Clear? So that is one explanation. Then if you look at this period, you can tell about the revolution period of the planet around the star. And also you can think about the mass, etc. Right? Again, as I explained to you, if you perform a computer simulation for all the possible parameter values of the system, and then you can find out something similar to explain your observation. And there are other methods like microlensing, imaging, etc. And there's one Ray Javadhan at Cornell University. He's the head of the department physics. He's a very close friend of mine. He's doing his area is exoplanets. He's actually the director of Carl Sagan Lab at Cornell University. I think you have heard of Carl Sagan, right? And his Cosmos series. I strongly recommend you watch this astronomy series, Cosmos by Carl Sagan. Now Ray Vijayawardena is, I think, 1 year junior to me. And he's the in charge of Carl Sagan Lab at Cornell. So I'm going to ask whether Ray can come and speak to you, right, about exoplanets, right? But I'm not going to do that if you do not interactively engage with the speaker. So if I haven't seen any interaction, any question coming at you, it's almost nil, right? So therefore, that doesn't encourage me to invite these people who are genuine professionals in the discipline. If I want to invite them, I need to make it fair by them, so that they also feel it's important to attend and speak to our students here in Sri Lanka. So I will decide on that probably later at time. I might invite him to come and talk to you, share his knowledge and experience about exoplanets. Now, let's look at the destiny of the planets, right? So where are we going from here? Number one, planets' orbits are chaotic over longer time scales. Chaotic. What do you mean by chaotic? Chaotic means you won't be able to predict it. Now we know we are going, Earth is going in a particular orbit, and all the other planets, they're also going in their own orbits, right? But in the long time scales, it would be difficult or maybe not very accurate to predict the future positions of the solar system, right? In all cases, this means that the position of a planet along its orbit ultimately becomes impossible to predict with any certainty, right? So that is what is called chaos. We don't know what's going to happen next moment, okay? After next few billion years, Mars, planet Mars. So Mars's eccentricity may grow to around 0.2. So it becomes elongated. It becomes elongated, right? Such that it lies on an Earth crossing orbit. So that is highly intimidating, scary situation. Planet Mars comes closer to Earth's orbit because it gets elongated, leading to a potential collision with the Earth. So we go around the sun 365 days, right? And if Mars's orbit is also nearby, then there's a high risk of a collision. But you don't have to worry right now. I'm talking about billions of years from now, right? There are other things. Mercury's eccentricity may grow even further. Mercury. And a close encounter with Venus could theoretically eject it from the solar system altogether. My God. In the future, right? Mercury's orbit, when it grows a bit elongated, just like what's going to happen to Mars, Mercury is too small to dictate terms in that area. So when you see the gravitational field structure, right, from the Sun, Venus, and Mars, According to mathematical models and computer simulations, it says there's a probability that Mercury will be taken out of that orbit and thrown out of the solar system altogether. So there won't be Mercury when that happens, right? There are so many other interesting things in long behold. It could um, be a possibility, right? If you look at Earth Moon system again, right? This is what I explained to you last week. Moon is facing towards the Earth, right? On one side. So this is the far side of the moon, near side of the moon. We have two names for that, near side and far side, because moon does not show the other side to the Earth. And sometimes you can, if you see the two photographs, we have the photos, right, of the other side, far side, is very ugly compared to the near side. And sometimes we might say moon doesn't want to show the ugly side to the Earth, right? So it's hiding the ugly side. There's so many craters on the far side, right? A lot of meteors, asteroids may have fallen on the far side, right? And near side is protected by the Earth. And if you get something like this, only it hits on the near side, right? But if you look at the area, the volume, huge area in this area, whatever comes towards the Earth, right, might get diverted and fall on the near side, sorry, far side. So probability wise, the moon sees high probability of getting an asteroid bombarded on to the far side is higher than the probability of the same on the near side. Okay, so this is what it is right now. What it is right now. So these are the two sides, near side and the far side. See, this is very, very ugly. It's like a battlefield, right? And near side is somewhat pleasant, right? You can see it. These are the seas and the other areas, right? So you have heard of tides, right? High tide and low tide. So this is basically because of the moon. You can see this illustration here, the moon and the Earth. Earth is not a completely solid body. There's a lot of water on the Earth. So this dark blue is actually the water body, exaggerated water body, right? So because of the moon's pull, you get this water to actually rise. Water level rises because the moon. Water is fluid. It's not attached to the Earth like tightly. So you get elongation over here. And because of the fluid dynamics, you can see the same thing going on the other side also, right? That's how it happens. Maybe not equal amounts, right? But somewhat. And also the Earth is also rotating like that. So the angular momentum of the liquid mass, water mass, okay? And here is the moon. So this side is low tide, this side is high tide. So that is why we see time to time water level goes up and down in certain parts of the world. The gravitational bulge here, this is the gravitational bulge, it is actually leading the moon because the Earth's spin is faster than the rotation period of the moon. Okay, so Earth rotates in 24 hours, whereas moon takes 27 and quarter days to go around the sun, the moon, sorry, the Earth, right? So this is very interesting dynamics. Okay. Now, what I really want to tell you is what's happening in the long behold, right? Uh, First thing, I want to explain you point by point because otherwise it's a complicated story. The first thing I want you to focus is this. The momentum transfers from Earth to Moon. Can you see that? Momentum transfers from Earth to Moon. So Earth has some momentum and Earth is spinning a bit faster than the Moon. Moon is coming behind. This is faster. So it looks like a mother taking her child for a walk. Okay, the mother is taking her child, son or daughter, 3-4 years old, can barely walk. The mother takes the hand and give a push. So actually, mother transfers energy to the child, right, to the kid, and pull her or him forward. This is something like that. This is the mother, this is the child, right? The earth is actually helping the moon, right, to catch up, right? So actually transferring momentum from the earth to the moon. So moon gets some sort of momentum, energy transferred from the earth through the gravitational coupling. So that's happening all the time. Even now it's happening. Okay. So when this happens, what happens is now Earth is losing its angular momentum. So we are losing the angular momentum. And Earth is speeding up. It's going slowly, but now it's going faster, like that. So gradually, Moon is getting faster. Okay. So this speeding up of the Moon is going around the Earth. It causes the Moon to spiral out and recede from us. So as you know, Moon is going around the sun, the Earth, right, on an orbit. But if Moon gets faster and faster, it will spiral out. Like if I draw it like this, spiral out like that. Okay. If the Moon slows down, it will spiral into like that. So it depends on the speed of the planet, the Moon, on the orbit, right? There's a particular orbital speed at which you are stable in the orbit. So you are not either spiral in or spiral out. You are going like a circle, right? Or ellipse. But if your speed increases from that orbital speed, you are going to spiral out. If you slow down, you are going to spiral in and eventually you will fall into the planet, main planet, right? So the moon's fate is basically spiraling out, and its orbit will grow bigger. So if you just continue this process, and if the Earth will last for about 50 billion years from now, right? Earth will not survive that long anyway, right? But hypothetically, if you imagine it is the case, there would be a day where both the Earth and the Moon will show one side to each other. Now, today, what we see is, right, from the Earth, if you look at the Moon, right? You will see on one side of the moon, right? You don't see the other side. But if you go to the moon and look down, you can see the earth, but you can see the whole earth because it's rotating. From the moon, you can see the whole earth, right? There's no kind of like far side and near side. So, but in the long behold, in the future, right, when this spirals in, it will go faster and faster and faster. Let's say it is still in that orbit, hypothetically, right? So when it goes faster, like say 24 hours, 24 hours, it goes one cycle. Earth is rotating also 24 hours. It won't be 24 exactly, maybe 20 hours, 18 hours, whatever, or maybe 30, whatever. It's a complicated matter, right? But there would be a time where you will see a dynamic clock between these two, some sort of synchronization. Rotation period of the Earth is equal to the revolution period of the Moon. Okay. Right now, there is some dynamic equilibrium. If you look at the Moon, its rotation period and revolution period are same. It has already achieved that. So what I'm trying to tell you is another dynamic equilibrium where Earth's rotation period is equal to the revolution period of the Moon around the Earth. So when that happens, right, only those people who are in that part of the world can see the Moon. Those who are on the other side of the moon, the Earth, right, will not see the Moon. They will never see the Moon. They will never see the Moon. Okay. So suppose this happens right above Sri Lanka, right above Sri Lanka, and we can see the Moon. All of the other nearby countries can see the Moon. But if you look at the other side, like US, for example, they will not see the Moon. Moon is not there in their sky anymore. So they have to travel to Sri Lanka just to see the Moon. It may be good for tourism industry. So these are the fancy stories, right? Fancy stories, just unlikely to happen within the time span of the solar system. But it's good story to tell so that the students can understand these dynamics. Otherwise, they think everything is like static. They are there forever. Nothing is changing, but things are changing slowly. And if you want to see a significant difference, you have to let it go and observe fairly long period of time. And we have to learn lessons, right? For example, our economy. Everybody took it for granted. No matter what they do, right, we're going to survive. Oh, this will not happen to us. That is what people thought. Okay. They played blunder after blunder after blunder, irresponsibly, without any accountability, without any quantitative analysis, very adamant, you name it, right? The top leaders, not only them, all the henchmen around them, even the cabinet, the parliament, everybody in that hierarchical system in the administration played a blunder after blunder after blunder. And nobody was speaking against it. Nobody actually raised their voice about what is going to happen. It was happening slowly, 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 slowly. And now we are in trouble. When we are in trouble, people shout out. Right? And a lot of people who were speaking against what was happening, they were part of the problem right from the beginning. It's too late for them now. It's too late because it doesn't make any difference now. Even though they speak against, right? They're part of the problem. So this is what I'm saying. In the universe scale also, things are changing slowly. So therefore, it will take some time for you to notice a significant difference. And because these things happen very slowly, nobody notices it sometimes, right? Nobody notices. Only the people who are there in the field can see it. And they explain to the others, this is what is going to happen if this continues like that. Okay? In a long time scales, you can see the difference. Otherwise, it looks like static. Nothing is changing. Okay, what else? What about Neptune and Triton? Triton is, you can see it over here. I think this is an actual photograph taken from Voyager, right? This is Neptune and this is the moon, Triton of Neptune. What is special about this? When a moon is revolving around a planet faster than the planet's rotation, there you have the exact opposite, right? The planet is rotating, spinning around its own axis, and there is a satellite which is going around the planet faster than the spin of the planet. Okay, this is the exact opposite of what we see here on Earth moon system, where the moon is going slower than the Earth. What we compare here is the spin of the planet and the revolution of the satellite. For the moon to go around the Earth, it takes about 27 days. And for the Earth to take one spin, it takes just 1 day, right? So this is what we are comparing. In here, Neptune and Triton system, Triton is faster than than Neptune. So therefore, this is like the kid is trying to pull the mother. Earlier case, mother was trying to give a walk to the child, right? Transferring some momentum to the child. But now this time, child is running away and pulling the mother along the way. So something like that. Then what happens? Momentum transfers from the moon to the planet. There you are. The momentum transfer is actually now from the moon to the planet, the opposite direction. So the result is the planet speeds up its rotation. Now, Neptune will speed up the spin. It will try to spin faster and faster and faster. And the moon slows down. The rotation period of the moon, right, extends, right? And this slowing down of the satellite around the planet will cause it to come closer and closer and closer and fall on the planet. Okay, so this is the destiny of Triton. So when a tiny body like a satellite over here, right, comes closer to a big body like the mother planet, it will start to feel different gravitational pull from the planet on either side of the object. So if I draw the object like this, and this is the planet is big, and this side you will see higher gravity, and this side you will see lower gravity, weak gravity. So therefore, you will see it fractures over here, right, at some point. So this is what is called the Roche limit. partial mean. It happens when the small object comes very close to the planet, right? One object, initially just one body, now two pieces, and then it becomes like four pieces, eight, like that. This is what happened to comet Shoemaker-Levy. When it came closer to planet Jupiter, it was broken into number of pieces. You just type in Google Shoemaker-Levy, you can see the photos of that comet falling onto the Earth, right? To Jupiter, rather. So let me show you some of these things. So I just pick it up from the internet. Shoemaker-Levy, you can see it over here, the planet and the comet, right? So I think most of the images over here are real ones, not a Photoshop one, I think, right? There you can see the fragments of the single body. Initially, it was a single body, but it was broken into pieces like that. And they fell on the planet one after the other. Okay. And also in some places, you can see the impact crater over here, right? The result, the remnant after the collision. So over here also, right? So to summarize that one, the satellite and the planet discussion, right? So this is what I can finally say. Tidal bulge stays directly under the moon. This is the third case. Sorry, this is not the summary. This third case. This second case. Third case is if the planet and the satellite, right, they have the same one-to-one dynamics. We call it tidal lock. Tidal lock. Say, for example, Earth is going around itself, spinning 24 hours, and the moon is going 27 days. We don't have the tidal lock. Okay. Neptune and Triton, they also don't have the tidal law. Okay. So if you have the tidal law, if I bring you back this one, you would see so this is the tidal bulge, right? A moon will be right above the bulge when it is locked. Okay. So it goes with the bulge, the spinning and this rotation, right? They're synchronized. So in that case, there's no momentum transfer either from the planet to the satellite or from the satellite to the planet. There's no momentum transfer. And it's a very stable system. So they can coexist longer time, millions and billions of years. They survive. Okay. That is why it is so important to reach the tidal lock. If you do not have the tidal lock, you are not stable. Simple as that. Either you go out of the planet altogether, or you will fall onto the planet sooner or later. So for an observer who is observing, right, you will not see you, right, in the long behold, because either you have gone out of the system or you have fallen into the planet. But if you reach a tidal lock, you are going to be spotted by an observer because you are there. So again, I'm telling you the same thing I was trying to explain earlier. What we observe today is only the leftovers. That is only the members who achieved the dynamic equilibrium, like, say, for example, tidal lock. All the other members, matter, objects, everything, have vanished. They were there for some time, and there was a day they became unstable and they were out of the system. And those who achieved, the small fraction who achieved the synchronization, like tidal lock here, continue to stay, and they are being observed now by observers. Okay, so therefore there's no surprise here. When you see these tidal lock and synchronization, there's no reason to question it. And I think I skipped a little part over here. This second case where the energy is transferred, energy transfers from the satellite to the mother planet. In that scenario, there are a lot more than just Neptune and Triton. But if you look at Phobos of Mars, it's also getting closer to Mars. And within about 30 to 50 million years, it will fall onto the planet. These are relatively small time scale. Triton of Neptune, this one. Metis and Adrastea of Jupiter, same destiny. They will all fall onto their mother planets. And at least about 16 small satellites of Uranus and Neptune. Okay, so scientists have tracked down their orbits, speeds, sizes, etc., and therefore they have pretty good prediction of what's going to happen to these satellites. What about Saturn's rings? One of the most fascinating things for kids who are fascinated about stars and planets. Saturn is the centerpiece, right? Because the rings and all. This, what you see here in the photograph, is not an artistic view. It looks like something that a painting or something, like somebody has drawn. No, this is actual photograph. This is actual photograph. This is not a painting or something, right? This is what is called the backlit photography. Backlit, right? Backlit photography. When you take photos, you shine a light and then take the photo, right? Flash. Otherwise, you don't see the details. There is a different type of photography where you shine the light from behind to see the details. Like when you show your X-ray to your doctor, this is what the doctor does. He has a light chamber and he puts the X-ray on the surface and turn the light on. It's a backlight. So backlit photography is different, right? If you look at the wedding photographers, they do both. They have a flash shining from the front, and also they have a little light from behind the couple, right? You don't see the light because it is covered, maybe right behind the groom's head or bride's head. It gives a little artistic impression, right? And here, the backlight source is actually the sun, our sun, and then you have the object that you want to photograph, that is Saturn and the rings, and the photographer is you here, right? Actually, it was one of the spacecraft that we sent out of the solar system. Cassini was the spacecraft. When it was passing Jupiter, it turned back and took these photos. Okay, so this is from very far away from the inner solar system. Actually, you can see Earth here, maybe somewhere over here, right? I recommend you go to Cassini mission and look at these photos in full size on the internet. Then the photograph description will let you know where to look at to find the small thing, Earth, right? Maybe somewhere over here. A little hazy something. We can't spot it over here. I'm trying to change the brightness and contrast level and see whether I can spot it. And I can't see it. Maybe somewhere over here, right? So we need to have the actual photograph on the internet. You can go see it. Probably somewhere over here. Okay, right. So we actually thought that Saturn has these rings and only these rings. And there's a small area over here, depleted matter, right? But now Cassini revealed there's another very faint ring, this one. Okay, the first time that we spot it. If not for Cassini, we wouldn't have known this, right? The existence of another ring around Saturn. That is the first thing I want to tell you. I think this photograph won a prize in that year, might be best prize or something, right? To get this photograph, you have to be there, right? So it's no competition. So I think they won the prize effortlessly, right? To bring the satellite or spacecraft there was a huge effort, but once you took the photo, there was no competition. And the observations revealed about 10 kilogram wide icy clumps of material that repeatedly break apart and reform, keeping the rings fresh. Wow. So we thought that these rings are going to get depleted, right? Going to get diluted and vanish. That was the speculation back then, before Cassini. But the Cassini revealed that there's a lot of matter, right, in this area, right, about 10 kilogram wide clumps of matter, and they actually kind of grinding out themselves and producing powder dust, right, to the rings, right, rather than they being like 10 kilogram wide matter. Now they are like powder, right? They provide these small particles into the ring system, and they brighten it up, they refresh or replenish the dust material in the rings. So therefore, we have changed the description now. What's going to happen to the rings of the Saturn? Now we say, no, the rings are going to be there longer than we had anticipated earlier. Okay. So I really wanted to discuss with you this kind of things. They are stories that you have not heard before. You have heard of Jupiter, you have heard of Saturn, Uranus, Earth, but what you have not heard of it is that Jupiter uh, is so big that it can take the center of gravity out of the sun. Okay. And Saturn, we thought rings were going to deplete. No, they are being replenished. And Saturn has a third ring. And Neptune and Triton is going to fall onto the planet. And Earth Moon system, Moon is receding from the Earth. I wanted to discuss with you that kind of thing. So it blows your mind away, right? Right. So finally, we come to the end of the story, fate of the solar system. But however, we are out of time for the day. So I will keep that for the next week. Any questions, please? Right. All right. So let's wind up for the day and I'll see you next time. Have a good evening.